Hi everyone, I'm Meng and I'll be presenting this PlatPal detecting malicious documents with platform diversity. So we all know that the malicious documents are now on the rise. They become a new tool for the attacker to spread malware. So for example, the APT28, the very recent attack attacks the hospitality sector, and the malware is spread by malicious documents. And also, Microsoft PowerPoint is now become a target, and now it can be used to bypass the antivirus software and to spread the malware. So, and also as the main reader for the PDF file, the Adobe Reader, there are over 100 CVEs reported in 2015 and more than 200 last year. And all the major components of this PDF reader, like the element parser, the JavaScript engines, etc., they have found the CVEs, and there are samples that targets those elements. So in summary, the flexibility of the document specification and a large attack surface, because the reader or the document reader is very complicated, and also less caution from the users, because users generally not expecting the document to be a malware, means there's more opportunities for attackers to profit. So we're all aware of this, and there's a battle against the maldocs. So like all the malware detection mechanisms, they can be generally classified into static and dynamic methods. So for static ones, there's a large number of work focusing on the JavaScript elements of the PDF files, and the other half of the works focus on the structure of the PDF files, like how many elements are there, like how they're organized within the PDF. So they use those as the features and to statically categorize or detect whether this is a malware or a benign document. And also on the dynamic side, there's a large chunk of work try to emulate or execute the JavaScript components in the PDF files. And also there's one work that try to enforce the memory using the memory access sequences to detect whether there's malicious activity happening. So, but if we look closely at these works, there are some interesting findings we can get. So the first thing is that there's a large reliance on the PDF parsers. So, and the PDF parser is not from the Adobe. It's different from the original PDF parser like Adobe uses. So we generally think that these external PDF parsers can provide the same functionality as the Adobe PDF parser, but it turns out it's not the case. So the last year in the SS, there's a parser-confusion attacks, which generally shows that the external PDF parsers are not capable of parsing these PDF files correctly, or at least as same as the Adobe readers. And also there's a large reliance on the machine learning, as say like many of the works uses machine learning to learn to categorize or to learn the features to categorize these benign and malicious document. But also last year in the SS, there's automatic ways to evade these classifiers. And also, almost all the works relies on known attacks. So they have to see the attack first before they can come up with the patterns or the signature to detect these kind of attacks. But what about 0 days? There's limited thing we can do about with these approaches. And the last thing, many works assumes that there will be detectable discrepancy between this benign and malicious documents. But actually, this might not be the case, because you can do mimicry and reverse mimicry attacks, which has both been shown in the papers. So as a highlight, the prior works relies on these 4 features, but each of them could lead to some drawbacks or some attacks. So what can we do in these cases? Can we come up with something that doesn't rely on these features, but rely on something else? So what PlatPal, the system we're trying to propose, want to achieve the following things. So we'll use the Adobe's own parser instead of external PDF parsers, and we'll try to use simple heuristics instead of the models learned from machine learning. And we'll try to be capable of detecting 0 days, which means that without any prior knowledge, we'll try to detect it. And we don't assume there's a discrepancy between the malicious and benign documents. And last but not least, we'll try to be complementary to prior works. So we'll not we'll try to raise the bar further for the attacker to create a malicious documents. So how do we come up with some kind of this kind of approaches? So let's see a motivating example. This is a 2013 example that targets the Adobe Reader 10.1.4, and you can download it from the VirusTotal. There's a hash. So actually, in the Windows system, if you open the PDF file, you will see that the heap spray is down, and this is the most important part. You will see that there's a string found, and the string found, which means that the exploit succeeds. And after that, after a few magic things, you will basically get arbitrary code execution. So this is how the attack works on Windows. But if you see the same documents, open the same document on Mac OS, you will see that, okay, it's initialized, the heap spray is also done, it's successful, but you cannot find this string, which means that a very critical step in the attack cannot happen. And I'll explain why. But this example kind of showed us an intuition that we can use platform diversity as a heuristic to differentiate benign and malicious documents. So basically, a benign document will behave the same when you open them across the different platforms, but a malicious one will show you some different behaviors. Actually, this idea has been explored by some inversion area. So like there are 4 inversion systems which try to introduce diversity and use this to detect whether there's a bad thing happening. But PlatPal is the first work that used the platform diversity, and there are some very unique questions we need to answer, like what do you define a behavior, and how do you define a divergence, how to trace them efficiently, and how to compare them without raising false positives. So let's see where we can find those behaviors. So a basic setup for PlatPal is that you will have the PDF documents. You will send them to different virtual machines. Each virtual machine has a different platform. So like one with Windows, the other with Mac OS. And you open the same PDF file with a PDF reader, and then you try to capture the execution. So there are 2 places we can capture the traces. The first place we call is an internal tracer, which is a plugin that resides inside the Adobe Reader. And when the Adobe Reader opens the file and processes the file, it will try to capture the critical functions during the PDF processing. For example, which elements is rendered, which script is executed, this kind of thing. And there is an external tracer which tries to capture the syscalls, which are basically the interaction between the Adobe Reader and the host platform. So by tracing this syscalls, we try to capture the impacts of this PDF file on the host platform. And a little bit details on the internal tracer. So the internal tracer, as we mentioned, is implemented as an Adobe Reader plugin. So it hooks those critical functions and try to emulate this PDF file processing as shown in the left. So, and because it's a plugin, it's a loaded library, it's very fast and very stable across the Adobe Reader versions. And in terms of the external tracer, it's basically a syscall tracer. And because the Windows and Mac OS platforms has very different syscall semantics, we are not comparing the raw syscalls. Instead, we'll try to aggregate the syscalls into 4 categories, like file system operations, network activities, whether there's new program launched, or whether this Adobe Reader crashes or exits gracefully. So this is how the external tracer is designed. And the general workflow is quite simple. You just have 2 virtual machines. You first restore a clean snapshot of each virtual machine, and you launch the Adobe Reader. Attach the tracers, open the PDF files, and this PDF file will be driven automatically by the internal tracers. And in the end, you dump the traces, and you have some external entity try to compare the traces and give you whether there's a divergence or there's consensus in the traces. So next, we try to evaluate the PlatPal. So we'll evaluate in 3 things. One is robustness. Whether the benign document actually behave the same across platforms. And we'll also evaluate the effectiveness, which means like whether there is actually differences of when you open the malicious document. And we also evaluate the speed and the resources usages. So for the robustness, so we collect 1,000 samples from Google search and 30 samples from some PDF learning sites. So these are all benign samples, and there are various features, like advanced features from the PDF specification are used. So we send those things to PlatPal, and we confirm that there is no divergence in those files, which kind of confirmed our first assumption. The benign documents behave the same. So the next we evaluate on the malicious documents. We collected 320 samples from VirusTotal, and we restrict to use the CVEs published in after 2013, and we also use the most recent version of the PDF reader when the CVE is published. This is try to emulate the case that at that time the CVE is a 0-day for that version of the Adobe Reader. So in general, there are 65% of the samples we actually see a divergence, either internal trace or external trace. And there are 11% cases that both PDF reader crashes at the same place, and also there are 24 cases where we didn't see a divergence. So this part is the most relevant part, because this could be the potential false positives of this PlatPal. So we do a further breakdown of this 24%, and then we find that like almost half of these samples targets old and specific Adobe Reader versions. That's why in the new versions or in the version we tested, we couldn't find or trigger this malicious behavior. So they just like go through as normal. And also there are like about 1/4 we guess that it could be misclassified by VirusTotal, because there are only one AV vendor classify it as malicious and mark it as with a CVE number. So we guess it might be the case. So there are also a few cases we cannot trigger the activities. For example, there's a CNC mechanisms, and the CNC server is down, so we cannot do anything about it. And there are a few samples we cannot find a concrete reason why this is we couldn't trigger the activity. It could be any of the reasons listed above. So in terms of the time and resources usage, every average detection time is about 20 seconds across both platforms. And the memory usage is about 2 GB per running virtual machine. But you need a lot of like disk spaces to host the snapshots. So some highlights from the evaluations, it kind of confirms that our fundamental assumption, which is benign documents behave the same while the malicious one will behave differently. And also the PlatPal is subject to the pitfalls of dynamic analysis. For example, the 24% of potential false positives, you need to prepare the environment to lure those malicious behaviors out. And also we incur reasonable analysis time, so we kind of think that this is practical. So let's do some further analysis and try to find what could be the root causes of these divergences and why platform diversity can be used for this detection. So we find 9 factors that are implemented differently across the platforms, and it's kind of related to how a malicious behavior or malicious activity is triggered. So in the first category, shellcode creation, we see that when you create a shellcode, you will face different syscall semantics or calling conventions or library dependencies across the post platforms. For example, the calling conventions are completely different on Windows and macOS, which means that if you're trying to use some ROP chain or some shellcodes, it's very hard to create the chain that works on both platforms without crashing. And also there's memory management some subtle memory management issues. For example, the layouts. For example, if you do an attack overflow and you want to override some target address, it's available entry per se. It's kind of the entry will be different on 2 platforms, and the offset will be different on the 2 platforms. And also the heap management mechanisms on Windows and macOS are completely different. For example, Windows has this segment heap, while the macOS uses this maximum malloc. So the trick that you use to grab this, for example, heap metadata, will be completely different, and it will work on one Windows. It will work on one platform, but probably not on the other. And also, there are some platform features which exist in one platform but doesn't in the other. For example, the supported executables. So say if you want to load something to run, it will likely to fail on one platform. So, and also there are file system semantics, we all know, and also the config and information hub, and also the expected programs you can find on each platform. So this could be the factors that causes this divergence when you try to launch some malicious activities. So, and back to the motivating example, so why it fails on Mac platform. So as we say that the PDF sample actually is a very complicated one. It tried to trigger some, to use some heap allocations to almost make sure that when you do allocation of the 300 megabytes BMG image, which is step 3, it will fall into some attacker control slot. And then you trigger this buffer overflow to override this heap metadata, which in the later, when you override this heap metadata in the later steps, and when you try to free that slot, you will actually free this slot 9 in slot 9 instead of the red slot. So, and then when you reallocate this 300 bytes, you will actually be placed in slot 9 instead of the freed one. And slot 9 is actually controlled by the attacker, so you gain this arbitrary read and write access on slot 9. But the thing is that given that Windows and macOS has completely different heap management, the heap metadata is stored differently, and the way you use to override this heap metadata will never work on macOS. That's why the step 4 fails, and in the example you see is that the string is not found. So as another case study, this is much more easier. So this is a JavaScript attack, and if you try to read something from this document or from this password file, it will never work on macOS because they don't have this /c things on macOS. And if we try to make it a generic step, like how we can use diversity to stop attacks, it actually can stop attacks in either the discovery step or exploitation step, or when you try to do some activities. For example, there are certain bugs that only exist in one platform, and those attacks that rely on these bugs will never succeed. And if you try to rely on some implementation bugs, and then you go to the exploitation stage, but if you try to launch some, say, memory corruption attacks, certain bugs, because of the heap management or the memory layout issues, almost all the attacks that succeed on one platform will fail on the other. And if you try to exploit some logic bugs, you might succeed on both platforms, but then you could be detected when you are trying to do some malicious activities. For example, when you try to execute the shellcode, load executables, or steal some files, or drop some exploits. You can be detected in those cases. And if you're really lucky, then yes, it's a success. We cannot detect it. And so how easy it is to bypass the PlatPal? Basically, you need to simultaneously compromise all the platforms in order to bypass it. And there could be some attack methods you can use. For example, heap feng shui, you can greatly increase the prediction accuracy, like how you expect the object to be allocated. And also there are heap spray and heap nopslat, which can also increase your accuracy of prediction. And also there are polyglot shellcode trampolines you could possibly use. But again, this is very hard to construct. And also, even if you succeed in constructing this, we can still detect you in the malicious when you're doing some malicious activities. So it significantly raises the bar for attackers. And also there are some limitations for PlatPal. For example, we couldn't handle this user interaction-driven attacks. We couldn't handle social engineering attacks because it all looks normal on two platforms. And also, there could be some non-deterministic sources like get time or random number generators we couldn't handle. But yeah, this is the time. This is also the thing we need to work in the future. And we could, in terms of how platform can be used, it's not very suitable for on-device analysis because you need to carry the snapshots and the large memory. But it could be best suited for the cloud storage providers, which can scan the documents periodically, or you can fit on the online malware analysis schemes like VirusTotal. And as a complementary scheme, we can also use PlatPal to improve prior works. For example, feeding the trace, the output from the internal trace to those prior works instead of using the external PDF parser. So in conclusion, we show that it is feasible to harvest the platform diversity for malicious document detection. We raise no false alarms and detects a variety of behavior divergences in malicious samples, and it's scalable, and there's various ways to deploy and integrate. So we'll release the source code soon at this link, so please check back. Thank you.
Thank you very much. Anyone with questions, please step to the microphone.
Feng Wei Zhang from Wednesday. So you mentioned a few root causes of the divergent problem.
Yeah.
And but this root problem seems like the benign applications will have the same thing, right? Mm-hmm. But I think from your assumption, it says blind applications they don't have this divergent problem. So I just wondering, in my opinion, for those kind of diversity, maybe we can increase the bar of the attacking, but is that really fundamentally can prevent attacks?
Okay, yeah, I agree, yes. So, yes, the correct argument is yes, we will try to increase the bar for attackers to create a successful attacks that works on both platforms. Yeah, we couldn't say that these are the cure, like say this is a prevention program. This is a prevention mechanism. You definitely cannot create such exploits. No, I cannot make such arguments. So yes, you're right. We try to increase the bar for the attackers, yes.
My name is Anant Karkar from the University of Virginia. Great talk, first of all. I have a two-part question first. In terms of both detection performance and overhead, mm-hmm. Have you looked at how this compares to machine learning-based classifiers that are built on top of dynamic features?
Okay. So in terms of overhead, what do you mean by in terms of overhead, but comparing stuff?
So by overhead, I mean like computational overhead. Obviously, these are dynamic analysis tools, mm-hmm. So mm-hmm. there's a little bit of overhead built in for actually running and looking at analyzing the files themselves at runtime. Mm-hmm. But then the additional overhead of this with having to run it in two environments as opposed to having maybe a machine learning model and the overhead associated with that. Is that comparison, is that something that you have looked into?
So first I would say that we're actually complementary to those. So it might not be very fair to directly compare with those. The second thing is that so in terms of what we're trying to do, I guess that the overhead for this is because we don't train models previously. We don't record any previous execution of things. So in that sense, we don't have any overhead, but they have to train the models and everything, and dynamically refresh the models. So in terms of overhead, then this is definitely a different story. But in terms of detection speed, yes, those machine learning ones should be very fast because they already had the model there. It's very easy to classify them with the model. So yes.
Thank you.
Yeah, quick question.
Hi.
I'm wondering why you do not choose Linux as a test platform. Usually people, I think, is more likely choose Linux, right?
Sorry, again, I didn't.
My question is why. I'm wondering why you do not choose Linux as a test platform.
Okay. So basically, Linux doesn't supply Adobe Reader after 9. So okay. we use Windows and Mac OS. But yes, I agree. Linux could be a very good source for this diversity.
Okay. So another quick question is, do you think currently the platform like Windows, Linux, and Mac the diversity is only 3, right? Not that high, I mean. Do you think this how to improve or what's the limitation for this solution?
Okay, so yes, in terms of this platform or the OSs, yes, there are only 3. But if you also think about these architectures, there could be ARM or Intel. So this is one way to also apply this diversity. Okay. So the other way of implementing this, addressing this OS diversity thing, is kind of, we have to agree that there are only like 3 major OSs, and but hopefully it will be like difficult enough for the attacker to create such attacks that works on all the 3 ones, and yeah.
Okay. Thanks.
We have time for more questions, so please go ahead.
Really quickly, and I came late, so if you answer this, I apologize. Would this same approach work on Word documents, PowerPoint, or is there a reason it's only PDF?
I didn't try on Mac on the Word or PowerPoints, but I guess it should work because Office has the same thing on Windows and Mac, and also you can develop those plugins there. So in terms of internal and external trace or the architecture, it works.
Thank you.
Thank you.
Great talk.
Thank you very much again.
Thank you.
And